Move on to section 5.3 about solving a quadratic trigonometric equation. Okay. So just like any algebraic equations, when you have it, you just typically factor that and solve for it. Right here, we use pretty much similar technique like how we solve the algebraic equations. Learning objective, using standard algebraic technique to solve trigonometric equation, solving trigonometric equation of quadratic type, solving quadratic equation involving multiple angles, and use inverse trigonometric function to solve the trigonometric equation. So first of all, to solve a trigonometric equation, we typically use standard algebraic techniques like combine like terms, factoring, something like that. And your main goal is in solving trigonometric equations to isolate trigonometric function on one side of the equation and get all the constant to the other side. And after that, solve for the trigonometric function. For example, if you have 2 sine x equal to 1, so you want to isolate sine x by dividing 2 from both sides of the equation. Then you get sine x equal to half. Now you can analyze the x to get the general solution. So typically for sine x equal to half, right, you can draw a unit circle here. Sine x equal to half. Sine x is positive in the first quadrant and second quadrant. So you're going to look for the angle from there. So we know that sine 30 degrees equal to half. Then the other one will be on the second quadrant. And if this is 30, then the other angle will be 150 degrees. So for 30 degrees is pi over 6 radian. 150 degrees, that will be 5 pi over 6 radian. So at least in the first revolution, you have 2 solutions, right? 2 solution. And if you subtracting 2 pi, adding 2 pi to that, and you're going to get a infinite many solutions. So general solution here should be pi over 6 plus 2n pi. Here n is the integer, or 5 pi over 6 plus 2n pi. Assuming n is integer. So we take care of all these coterminal angles. Okay. Yeah, so that's what I'm talking about. So you have 2 solutions, 2 general solutions, by adding 2n pi to the solution in the first revolution. So now, just like I will show you, solution 1 is from the first quadrant, solution 2 is from second quadrant, and you can use the coterminal angles to determine those 2 angles, and also the general solution come from coterminal angles. General solution come from coterminal angles of 5 pi over 6 and pi over 6, and they both yield the same result of half. Okay, so typically when you're solving a trigonometric equation, you write the answer you're using exact values rather than the decimal approximation. So keep as it is. Okay. Now let's take a look at this trigonometric equation. So here we try to solve for x. So first of all, when you have sine x plus radical 2 equal negative sine x, so we're going to combine the trigonometric function by adding sine x from both sides of the equation. Cancel that, get 2 sine x plus radical 2 equal to 0. Now subtract radical 2, isolating the trigonometric function. So we have 2 sine x, 2 times sine x equal negative radical 2. I'm going to divide 2 from both sides of the equation. Then you get sine x equal to negative radical 2 over 2. And now we're going to draw the unit circle. Let's analyze this. So now sine is negative in the third quadrant and the fourth quadrant. So that means our angle must be in the third and fourth quadrant. And for radical 2/2, that must be 45-degree angle. So this is 45 degree. So this angle will be 180 degree plus 45. So one of the solutions will be 45 degree plus 180 degrees. So that turned out to be 225 degrees. And if you turn into a radian measurement, will be 5 pi over 4. And again, if you want to get a general solution, you're adding 2n pi to that. Okay. Second solution is 360 degree minus 45 degrees. That turned out to be 315 degrees. And if you turn 315 degrees using the conversion, it will be 7 pi over 4. And in order to get a general solution, you add 2n pi. So you have two general solutions, this, that. So the answer, general solution, x equal to 5 pi over 4 plus 2n pi. Or the other type of general solution will be 7 pi over 4 plus 2n pi. Oh yeah, typically draw the unit circle. They'll help you, to figure out where the angle is located. And we can have quadratic equation. For example, like this, like in a quadratic form, right? Ax squared plus bx adding c equal to 0. So first example, we get 2 sine x squared minus sine x minus 1. You can also think of this as 2x squared minus x minus 1 equal to 0. Right? They are similar. The only thing now, the variable becomes trigonometric function. And basically you just factor like 2 sine x, okay, and a sine x minus 1 plus 1 here. Just like how we factor 2x squared minus x minus 1, it will be 2x plus 1 x minus 1. And from there you set each linear factor equals 0 and then solve for the unknown. Similarly, second question here, secant x squared minus 3 secant x minus 2. You can also relate it as x squared minus 3x minus 2. So if you want to factor this, that will be x. So actually this is not factorable. That means we gotta use quadratic equation. Okay. So you can also use a quadratic equation to solve for the secant x here. Okay. But yeah, that's exactly what this is. Now factoring, quadratic equation, then you solve it using quadratic formula. Now let's take a look at the one we just go over. Similarly, we're assuming 2 sine x squared minus sine x minus 1 equals 0. And you want to find all solutions within the first cycle. 0 to 2 pi is for the first cycle. So first of all, factor this. So you do 2 sine x sine x. I'm going to show you the general method I usually do is by breaking down 2 sine x squared. So you get 2 sine x and sine x. So break down the first term. First term goes here. And break down the last term, we get -1. So one of them got to be -1, one of them got to be +1. So that's the last term. So now let's confirm the middle term, sine x, by cross multiplying. So you get -2 sine x times 2 sine x times -1 is -2 sine x. +1 times sine x is sine x. 1 sine x. Combine them, you get -1 sine x. That matches with the middle term here. So that means you have the right factoring. So that should be 2 sine x plus 1 and sine x minus 1 equal to 0. And now we have two linear factors, so setting each one of them equal to 0 and solve for the angle x. Yes. First one, subtract 1 from both sides of the equation, we get 2 sine x equal negative 1, and divide 2 from there, sine x equal negative half. Second one, adding 1 from both sides of the equation, we get sine x right away equal to 1. So if you draw the unit circle, for sine x to be negative half, the reference angle must be 30 degrees. Okay. And it's located in the third quadrant and the fourth quadrant. Sine negative in the third quadrant and fourth quadrant. The other one is 30 degrees. Okay. So the angle x here for the first one should be equal to, it's 180 plus 30, so it's 30 plus 180, 210 degrees. The other one is 360 degree minus 30 degree, it turned out to be 330 degrees. Okay, and for sine x equal to 1, sine reaches 1 on the 90 degree angle, right? So x equal 90 degree. So if you turn both of them, all three of them into the radian measurement, 90 degree equal pi over 2. 330 degrees equal to 11 pi over 6. 210 degrees equal to 7 pi over 6. So three solutions within the first cycle. Again, sine x equal negative half. Okay. So 30 degree yields negative half, and then this is symmetrical. That means this is 30 degree. And now, first angle is 180 plus 30. Now to 110 degrees. And 210, if you turn into a radian measurement by setting up the proportion, will be x over 210 degrees. So 180x equal to 210 times pi. So dividing 180 degrees from both sides of the equation, so you get x equal to, reduce it, it will become 7 pi over 6. Yeah. That's why the first solution is 7 pi over 6. Second solution is in the fourth quadrant, so x equal to total 360 here. That's one cycle. Reference angle 30 degrees, so 360 minus 30 degrees, 330 degrees. And similarly, using the proportion to convert it, so pi over 180 degree equal to 330 degrees x. That means 180 x equal to 330 pi. And dividing 180 from both sides of the equation, x equal 330 degrees pi over 180 degrees. Reduce it by 30, becomes 11 pi over 6. So two solutions from the first factor. Second factor is sine x equal negative 1. No, equal to 1. Yeah, positive 1. So in the first cycle, sine x equal to 1 right here, 90 degrees. That means x equal to 90 degrees. 90 degrees, half pi. Pi is 180 degrees by 2, that becomes 90 degrees. So three solutions for this question. Sometimes the functions involving multiple angles. Next example involving a trigonometric function of multiple angles in the form cosine KU or tangent KU. First of all, solving the equation for KU, and then after that divide the result by K, by a constant. K usually is a constant. Now, look at this. We get 2 cosine 3t minus 1 equal to 0. This is in parentheses if you want to make it more clear. So first of all, you want to isolate cosine 3t by adding 1 from both sides of the equation. Let's get 2 cosine 3t equal to 1. Now dividing both sides of the equation by 2 to isolate cosine 3t. Cosine 3t turned out to be half. Now you draw the unit circle. We know that cosine is positive in first quadrant and then fourth quadrant. So cosine 60 degrees equal to half. So it means reference angle must be 60 degrees, symmetrical. So this is also 60 degrees. So we have two solutions. First one is 3t. First solution is 3t equals 60 degrees, right? Second solution is 3t equal to 360 minus 60, which is 300 degrees. So 3t equals 300 degrees. Okay. Now if you turn into a divide 3 here, t equals 20 degrees here. 20 degree you turn into a radian measurement, it'll be pi over 9. 180 over 9, that's 20 degrees. The other one is 100 degrees, dividing 3 from both sides of the equation, t equal to 100 degrees. 100 degrees, that's 5 pi over 9. You again using the proportion to convert it into the radian measurement. Right, so t equal to pi over 9, t equal to 5 pi over 9. Well, so for the general solution, you're just adding 2n pi, right? So t equal to pi over 9, adding 2n pi, or t equal to 5 pi over 9, adding 2n pi. Here n is an integer. So cover all the possible solutions here.